It's my pleasure to be here today to talk to you about our research on the premature aging disorder, progeria, and its relationship to normal aging. So aging is sometimes thought of as a gradual, inexorable decline. And that is nicely exemplified here in this photo series by Nick Nixon, who photographs his wife and her 4 sisters every year over a period of years starting in 1975. And you can see these gradual changes. But the premature aging disease, Hutchinson-Gilford progeria syndrome, called HGPS, or just progeria for short, really suggests a more nuanced view, as you can see looking at these very sweet and brave and unfortunate kids who have the disease progeria. So this view suggests that there are certain pathways that can very suddenly turn on and promote a rapid aging pathway. So this process, at the heart of it are the 2 molecules shown here. So, excuse me, let's get the pointer here. There we go. So we'll go from A to Z. As Steve mentioned, the A molecule is lamin A, a nuclear scaffold protein. And Z is the zinc metalloprotease, which I'll just refer to here as ZMP. And what we know is that lamin A is made in a precursor form. It has a lipid attached to it called farnesyl. Now, many proteins in our body have this same lipid attached, but for all of those proteins, the proteins need that lipid for their biological function. And lamin A is a bit different because it undergoes a cleavage event, and that's mediated by ZMP. So we don't know why cells go to the trouble of modifying lamin A and then cleaving off the last bit. But we do know that this is important for normal human health. And that's because this is the step that fails to occur. When it fails to occur, gives you progeria. So this is Sam Burns, a child with progeria, a rather amazing kid. He unfortunately died a few years ago. And Sam has a mutation in his lamin A gene, I don't know if you can see that, that prevents cleavage by ZMP. That causes his nuclei to be quite misshapen throughout his body. Sam's mom, Leslie Gordon, and the founder of the Progeria Research Foundation, is unaffected, and her nuclei are normal. And we now know that progeria can result from either mutations in lamin A that fail to cleave, or in the scissors themselves, ZMP. And these give a series of related progeroid disorders. And I will mention, actually, if you're interested, Sam did a TED Talk in 2013. It's quite inspiring, and it's called My Philosophy for a Happy Life. It's had over 29 million views, and I highly recommend it. So I mentioned the nucleus, and here we can see lamin A sitting under the nuclear envelope. Forms a meshwork scaffold type structure shown here, and that supports the nucleus. So it's not surprising that when this goes awry, we have misshapen nuclei. And my lab has really been focused on trying to understand lamin A, trying to understand ZMP. We discovered this molecule in baker's yeast many, many years ago, long before there was any connection between lamin A and progeria. It was an interesting protease. It has many interesting properties, so we simply study it as basic scientists do. and learned that it is indeed what cleaves lamin A. But still, we didn't know about progeria. Likewise, there are not many people in the early days who studied progeria. HGPS, or progeria, was described in the late 1800s by two doctors who had patients, Hutchinson and Guilford. That's where it gets its name. And it's a very rare disease. The incidence is 1 in 4 million. So there are many features of accelerated aging, including thin skin, failure to grow, loss of body fat, loss of hair, joint and bone defects. But in particular, these kids have blood vessel defects in the form of early onset and very aggressive atherosclerosis. And ultimately, they die in their mid-teens from heart attack or stroke that results from this atherosclerosis. Now, again, these researchers were, the early researchers studying progeria were unaware of lamin A and ZMP. But a key advance in the field came in 2003 when two laboratories, Francis Collins in the US and Nicholas Levy in France, showed that progeria maps to the lamin A gene. And what this did is it brought together many disparate fields and allowed us to really make rapid progress. And that's exemplified by this example. So here's that processing pathway I mentioned. Sorry. All right. And we learned from studies of the disease that this permanently farnesylated form of lamin A was really the culprit that caused disease. And in particular, it's this farnesyl molecule right here that is the problem. And fortunately, we knew, and the field knew, or what became a field actually, that there was a drug called farnesyl transferase inhibitor. And that drug had been developed for other purposes and could now, we felt, potentially be repurposed to help patients with progeria. So we carried out the studies shown here where we could show that the nuclear morphology defects of cells were corrected by an FTI. There were others who studied mouse models as they came along and showed that progeria can be lessened by the addition of FTIs to the drinking water. And ultimately, this is really a bench-to-bedside story that led to clinical trials that were published first in 2012 and then just recently, last month, that showed that FTIs help improve the lifespan and health span of children with progeria. It doesn't cure the disease. It buys these kids a few months, a few years at most. But it's a start. So this is a picture of my mother. And she's 100 in this picture. She lived to be 104. And I would wager to say that her ZMP is very robust and is cleaving lamin A very well. But obviously, if this process fails, especially late in life, it can hasten the aging process potentially. So our current work is focused on really understanding more about ZMP mechanism so that we can prevent any failure of this. And we think our studies will help for premature aging as well as normal physiological aging. So you wouldn't want to take a drug, for instance, that inadvertently inhibits this enzyme. So our basic studies are focused on novel aspects of ZMP as a protease. I won't go into them here, but just to give you a sense that we are studying disease mutations in progeria, These have helped us learn more about the mechanism of the protease. And this, in turn, this information has given us some clues to some personalized medicine potential approaches which could help certain, not all, patients with ZMP-based progerias. In particular, we have some interesting results with this mutation, and we're now exploring it in patient cells. So finally, I just want to conclude by saying that progeria is likely to provide insights into the atherosclerosis of normal aging. So why do I say that? Well, atherosclerosis, as you know, involves deposit of fatty plaque in the arteries and occludes the arteries. And there's a timeline for atherosclerosis, which involves unobstructed vessels when we're young and in our first decade. And by the time we get into our 40s and 50s and older, even normal people can have significantly occluded vessels. So, in fact, aging is the greatest risk factor for atherosclerosis. Now, in progeria, the onset of atherosclerosis is hastened by several decades. And these kids have very aggressive atherosclerosis, starting when they're very young, despite the absence of any known risk factors. They don't have high cholesterol and so on. So we feel that progeria likely reveals a vulnerability in blood vessels. And if we can learn at a molecular level what pathways are specifically affected by that permanently farnesylated lamin A, that may help us to not only understand, of course, more about progeria and devise new treatments, but also may help us all ultimately age in a more healthy fashion. So, as you know, research takes a village, and here's my village. And we have a number of collaborators involved in this work. So thank you.
Questions?
Hi, Laurel Oldock, ASBMB. Could you explain a little more, please, why lemon farnesylation alters nuclear morphology so much?
We don't actually understand the details of why the nuclear morphology is so altered by that permanently farnesylated lamin A. That's a subject of study. And in fact, we don't even really know what the consequences of altered nuclear morphology are. But we do know that that is a very useful signpost, hallmark for disease. And that is something that we can measure. So all of the different aspects of the disease, and I think it's an important point you're getting at, what all is happening at a molecular level is not clearly understood. And it's important to figure that out because any points in the pathway can be a target ultimately for intervention.
I have one. Are there any signs of chronic inflammation in the children with progeria?
I don't think that has been looked at carefully enough. That has not been one of the signposts that's reported. But these kids have numerous defects. And I think a challenge in our field is to link the particular defect with really that disorder. Is the molecule causing inflammation? There is some mitochondrial dysfunction, for instance. There are other signposts of aging.
That's terrific. Thank you very much, Susan.
Thank you.